Hey guys! Alright, today we are going to talk about colligative properties. And when I say we, I mean me and you and little baby Juniper here. See how teeny weeny she is. So, colligative properties, this is the reason why we put salt on the roads. This is why when they boil sap to make maple syrup, why they use a thermometer to do that. So basically, colligative properties are the effect that a solute has on a solvent's physical properties. In the case of salt on the road, remember that reading that we did a little while ago? We put salt on the road to lower the freezing point of water so that it freezes at a colder temperature. So it has to be really, really cold in order for water to freeze. So that way we don't, and out we go. And also, the more water we boil off, or the more concentrated it gets, the boiling point actually goes up. So the freezing point goes down, but the boiling point goes up. I like to think of it this way. The freezing point is cold, so it just gets colder. The boiling point is hot, so it just gets hotter. And so when we're making maple syrup, they say boil it till it's such and such a temperature. And basically what they're doing is measuring concentration indirectly, because the greater the concentration, the greater the boiling point. It's also when you make candy, if you can like basically take sugar, water, and a little bit of like corn syrup. You mix it all together and boil it till it's 300 degrees. Scoop it out of your pot, blop it onto like wax paper or something. You get That's basically how you make hard candy. You measure the concentration by the boiling point. So here's the deal. The colligative properties are the effects solute has on the solvent's physical properties. And what's neat about this is that it depends only on the number of dissolved particles. It doesn't matter what it is, just how many particles are dissolved in the water, because those particles like physically interfere with the physical process of freezing and boiling, kind of like get in the way of that. And that's kind of how it interrupts it and creates these things called what we see called the colligative properties. The identity of the solute, in other words, what it is, doesn't matter. It can be salt, it can be sugar, it can be actually in Vermont. They used whey, which is like the liquid leftover from when you make cheese. They sprayed whey on the ground, and it was great to prevent ice buildup. And the reason they did that is because the salt actually is starting to pollute our waterways. Like the amount of salt in our fresh water, like waterways, is actually like getting to be a little bit out of hand and unhealthy for like the local biodiversity. So Vermont was like, well, we got all they make. Dude, Vermont, they make cheese. They're like, what are we gonna do with all this whey? They used to just dump it out in the field. They actually use it to, in some areas, to help like de-ice the roads. So what it is doesn't matter. Again, it's only the number of dissolved particles that is it. And the solute isn't affected. So like the salt that you put in just stays salt. Nothing happens to it. It doesn't know. There's no weirdness. The only thing that changes are the freezing and melting point of the solvent, which is fun for us because then we can do things like make maple sugar and stuff like that. Which, lordy, why wouldn't we want to? All right, so here's the thing. Changes in boiling point. Like I said before, the boiling point is high, so it just gets higher. And of course, we need to measure this because that's what we do. We measure stuff. And 1 mole of dissolved particles into a liter. You know about how much a liter is. It's like a 2-liter bottle, right? Half of that. That's how you buy soda. A 1-liter soda is like the super big ones. Um, raises the boiling point by only 0.52 degrees centigrade, which is like 1 degree Fahrenheit, which means that it boils hotter with dissolved solute. And now I'm going to ask you, there's an old wives' tale that says if you add salt to water, it boils faster. Once you look at that down there, and you tell me if that's a legit old wives' tale or if that's just, loopy doop. It, Guys, it's loopy doop, man. It actually has to boil hotter, so technically speaking, it'll take longer because you've got to get it hotter. Who cares? Who's counting? I'm not. Freezing point. As I said earlier, the freezing point is cold, so it just gets colder. But the effect of freezing point is far more significant. If you'll notice down there, um, it decreases 1 mole of dissolved particles decreases the freezing point by 1.86 degrees centigrade, which is a significant difference. So if you get the roads really salty, you can lower the freezing point of water by several degrees, which is great. The problem is that there is a limit to this. There is a the water will still freeze. So when it gets super duper cold out, you'll notice that the trucks will stop salting and they will use sand because the salt simply stops working because the colligative properties can only lower the the freezing point of water so much because once you have a saturated solution, you can't dissolve anymore. And colligative properties depend on the amount of dissolved particles. So once you hit saturated water, the effect doesn't really change anymore, and they got to switch over to sand. So like I said, freezes colder. Boiling point hot gets hotter. Freezing point cold gets colder. And look, I've got a thing. I look. I'm getting the pointing thing down. Boop boop. All right, see, I just drew this on Google Docs. I'm fancy and becoming technologically savvy. So look, as you go to the right here, right, as you move to the right and you get more and more dissolved particles, right, you have a greater concentration. That means that the boiling point gets higher and higher and higher, right? So whatever concentration gives you the most, or I'm sorry, whatever situation gives you the most dissolved particles or the greatest concentration, it will give you the highest boiling point and it will give you the lowest freezing point. Now, same thing, but vice versa, because the regions are not going to be nice to you and make any sense whatsoever. They're probably going to be like, okay, what conditions give you the lowest boiling point? Because that we're all thinking about going this way. So they're going to ask lowest boiling point. Well, that's way over here. So yeah, like over here, or over here. That's going to be the lower concentrated, the fewer dissolved particles. Same thing, freezing point, only again, except same thing, except completely opposite. The greater the concentration, the more dissolved particles, the colder it gets, the lower the freezing point. In other words, the colder it has to be in order to freeze. And then vice versa, the lower the concentration, the fewer the dissolved particles, the higher up the freezing point will be. So if you have pure clean water, it will freeze right at zero. The instant you put anything into that water or dissolve anything into that water, it has to actually get below zero in order to freeze. Dig? Doug. All right, so moving on. It's not going to be just that simple, right? Because there's more than one kind of stuff. We have two categories of stuff in our world. We got molecular stuff and ionic stuff. Let's go with molecular stuff first because that's easiest. Now, molecular, I don't know if you remember, but it means covalently bonded, and for us, it'll be carbon-based because we're going to keep it simple right now. Carbon-based things are covalently bonded. That's what we're going to start with, and their effect is like not so great because here's the deal. If 1 mole of a molecular substance is added to water, 1 mole of particles is produced. In other words, the molecular things, carbon-based for us, it doesn't break apart. It just stays as one thing when we dissolve in water. So you take one sugar molecule, you put it in water, and you got one sugar molecule floating around. You dig? It looks like this. That's sugar, right? You take one sugar. Do you see how it's carbon-based? Look at that. Boom, carbon. Molecular, covalent, does not break apart when you dissolve in water. It only makes 1 mole of dissolved particles, right? It's not that effective, which is why we don't use sugar on the roads because not as good. Because look, ionic stuff is different. So for ionic things, if 1 mole of an ionic substance is added to water, you will get more than 1 mole of substance. For example, let's look at this one. Boop. Right? You see how if you add one NaCl, one particle of sodium chloride, you put that into water and the water breaks it apart into 2 particles. So now you got 2 particles floating around doing twice the colligative effects of your water. So that's why we like to put like ionic things like salt on the road. And road salt is not just table salt. It's all kinds of salt. And you'll see why. Because look, what if we used H2SO4? I don't actually recommend using H2SO4 because that's sulfuric acid. It will melt the road, but it still has colligative effects. And if you look, see, you got 2 hydrogens, so you make 2 hydrogen ions. There is 1 SO4, so you make 1 SO4. So in all, you start with 1, and you end up with 3 particles in all after it dissolves. So you have a triple whammy effect with something that makes 3 ions. Dig? Doug. The ionic substances break apart, yielding more particles. And that is what is clutch right there. More particles because they break apart. Okay? Now for the mathy stuff, because you know that we got a math, and I don't. Oh, you know I'm not going to use my brain, right? I'm using this because that's all yeah, there's no way I'm doing brain stuff here. So the question is, what will the boiling point and freezing point of water be if we added 1 mole of the following to 1,000 grams or 1 liter or 1,000 milliliters, all the same thing, of water? And I put right down here a little reminder that the boiling point is going to increase by 0.52 and the freezing point is going to decrease by 1.86. I can't even remember. It'll be given to you. It'll always be given to you, so you don't necessarily need to remember that. But here's what I do need you guys to be able to do. I need you to look at this. Dig? Carbon-based. Is that going to break apart? I'll give you a minute. Olive, is that going to break apart? If it's carbon-based. Wait, ask Juniper. The answer is no. No, it's not going to break apart. So 1 mole of this sugar is going to give you, guess how many? You said it, 1 mole of dissolved particles. So the freezing point, negative 1.86. Because remember, you start at 0 and it goes down. It decreases by 1.86. And the boiling point, now remember, what is the boiling point of water? Say 100. Say 100. Say 100. Just, right. Water boils at 100 degrees, and then it increases it by 0.5. That's 2. So it will be, I don't like that. That's ugly. Yeah. You see how that works, guys? You dig there? So now this one, let's come over here. NaCl. It's ionic. How many ions will that make? I'll give you a minute. That's right. This will make 2 dissolved particles. So this will be not 1.86, but 1.86 times 2. Yeah. And then this, because it's going 2 steps up, 1 step 5.2, 2 steps, you dig? Because it went up 2 steps. This one, CH3O. You know how that do. Carbon-based. 1 mole to 1 mole. You're taking 1 step down. You're taking 1 step up. Now this one, NaOH. You see that right there? See how that's a polyatomic ion? You see that that's an ion because it's on the reference chart. You know that. Guess how many particles? 2. So if this made 2 particles, 2 steps up minus 3.72. And since I already did the math, 101.04. Super easy, right? Now the last but not the least is this one, calcium nitrate. We love it. It burns so good. It makes a pretty flame. What we've got here is, I see that, oh wait, polyatomic ion. Did you see how I said the word ion? Right, so it's going to be ionic. So I've got 1 calcium. See how there's 1 calcium there? And I've got 2 nitrates. Do you see how there's 2 NO3s there? You see that? 2. So I've got 1 calcium and 2 NO3s. How many dissolved particles in all? Yeah, good. Nice. So what I do for my freezing point is I take this 1.86, I'm going to multiply it by 3. Well, my thing is going to multiply by 3. And it's going to tell me 5.58. All right, so 3 particles, 3 steps down. For this one, 3 steps up. Ooh. You dig? All right, I'm just about out of time for my first video. More to come, you guys. Oh, by the way, this is the end of the chapter. Hold on tight, because I'm coming up with some way. I'll figure something out.